Video is going to cover a quick application of orthogonal diagonalization of a matrix. We're going to start by talking about something called quadratic forms. And the definition of quadratic form is something that is ax squared plus bxy plus cy squared. That's basically all the possible degree 2 terms in x and y. And a quadratic form is going to be associated to a quadratic equation where we put all things that are degree 2 or smaller here, set it equal to 0. And notice that these quadratic equations in two variables, these are something that you should have studied in a previous math class. And if you look at the graphs of them, they're going to be something called conic sections. And there's a few possibilities here. You could have a circle. You could have an ellipse. You could have a parabola. And you could have a hyperbola, or the degenerate case where you have a line. Regardless, this is what we're looking at here. And when you took your algebra class where you studied these, you learned some of their equations. Like a circle is going to be like x squared plus y squared is r squared. An ellipse is x squared over a squared plus y squared over b squared is 1. A parabola is something like y is x squared. And a hyperbola is going to be something like x squared minus y squared is 1. I mean, I can put in the generic a's and b's here, but regardless, these are the shapes you're going to be looking at. However, if you recall when you did these, none of these had an xy term. So if I ask you to graph x squared plus xy plus y squared equals 5, the stuff you learned in algebra class would not be sufficient to solve this. You would not know how to graph that unless you had a particularly advanced algebra class. But the thing is, there's actually a really nice way to get rid of that xy term in order to identify what the shape is without that. And what we're going to do is we're going to rotate our axis. So the xy term, when you do that, I'm not sure exactly what the shape is, but what's going to happen is it's going to take your ellipse or whatever it may be, and it's going to tilt it. It's going to be off at an angle rather than on the xy axes. But it turns out there's going to be a nice way to kind of tilt it back, and then once we have that, we can identify which equation it's going to be that doesn't have the xy term in it. So first things first, notice that we can take our quadratic form and rewrite it in this matrix format here, where we have the x vector is our variables xy, and then this A is this weird A, B over 2, B over 2C matrix here. And you can believe me or you can work it out yourself, but if you multiply all three of these things out, you're going to get ax squared plus bxy plus cy squared, and there you go. Well, this matrix right in here, that is a symmetric matrix, which means it's going to be orthogonally diagonalizable. Okay, if it's orthogonally diagonalizable, we can rewrite it in this format. And it's going to turn out that if we choose our new variables to be x prime, y prime, and we relate them to the original variables by being p times xy, or in other words, if you think about solving for your original variables xy, and it would be p inverse x prime y prime by just multiplying by p inverse on both sides. And then remember that this is orthogonal, so the inverse is the same as the transpose. And if you were to take this and replace it in for the vector x here, what you're going to end up getting there is you're going to be getting the ax squared plus bxy plus cy squared. It's going to be x prime y prime times the diagonal matrix times x prime y prime. And if your two eigenvalues are, say, lambda 1 and lambda 2, you'd have lambda 1 x prime squared plus lambda 2 y prime squared. And what that means is you're able to rewrite the equation here without the xy term in it, so it's no longer tilted, and you can then identify what shape it's going to be. So let's look at a specific example here. We're going to look at x squared plus 4xy plus y squared equals 49. At first, we probably don't know what shape that's going to be because of the xy term there. So our a is going to be 1, my b is 4, my c is 1. So then my matrix A, b over 2, b over 2, c is going to be 1, 2, 2, 1. And then we need to orthogonally diagonalize this matrix. Conveniently, in my last video, I already did that. It's the following here. My D was 3, 0, 0, negative 1, and this is going to be my P transpose. And then what I show you here is that the original quadratic form, ax squared plus bxy plus cy squared, can be rewritten in new variables x prime, y prime by using the lambdas, which are the eigenvalues. So that means I would have x squared plus 4xy plus y squared is 49. This left side is going to become 3x prime squared and then minus 1 y prime squared equals 49. So this is my new equation here where I've gotten rid of the xy term there. It's no longer tilted, and it's just based on the eigenvalues. And based on that, we look at our shapes here. This is going to be a hyperbola. It's going to be a hyperbola because of that minus sign there. If they were both plus, it would have been an ellipse. Regardless, we now know this is a hyperbola, and if you really wanted to, you could try to graph it using things you learned from college algebra. I'm not really big on having students do that, but you could. The main thing, though, is that by doing this, we're able to identify what shape it is, get rid of the xy term, and make the problem much simpler. I do want to give you one warning here. If, and only if, you have other terms here that are not part of the quadratic form. Remember, the quadratic form is just the things that are all degree 2. So if I had like a plus 5x or something that was degree 1, I have to actually figure out what that is using the fact that my xy is P transpose times x prime y prime. So I would have had to take this matrix P, transpose it, multiply it by x prime y prime, and then I could solve for what x is and I could plug that in. It's an extra complication. I wouldn't worry too much about it. We're just trying to get a brief idea here of what quadratic forms are and how we can do this orthogonal diagonalization with them. But if you had to do some random problem, you'd need to know how to do that.